So current carrying loop means you know this, right? So at this point, what did we find? B is equal to mu naught by 4 pi 2 pi a squared plus x squared power 3 by 2. Anybody having any issues? And then the current, right? This is what we found earlier. If I say, for example, if I assume x is very big compared to a, right? Let's say this is like, say 20 centimeter. Maybe this is like only 1 millimeter, right? So that means it's going to be very small compared to this length. So that means this is very big compared to this. Okay. So if that's the case, what can I do? I can ignore a square because a is very small. I'm assuming what will happen if this was small. Okay. That means this is gone. X square power 3 by 2, 2 cancels, x cube, right? So I will say mu naught by 4 pi I 2 pi a squared by x cube. Anybody having any issues here? But what can you say about pi a squared? This is the radius. So pi r squared. What is pi a squared? Or pi r squared? Area. So this can be written as area. This part. This I'm going to cancel it now. So this and this will cancel to 2. So we'll get mu naught by. Actually, I don't want to cancel this. Let me keep it. So mu naught by 4 pi I into area 2 area divided by x cube. What can you say about I into a? What is I into a? M, yeah, right? M is equal to IA. So that means I can say mu naught by 4 pi. So since I into a can be written as 2m by x cube. So this is my magnetic field B. Anybody remember the electric field due to electric dipole on its axis? One by 4 pi epsilon naught 2p by r cube. Anybody remember that? It is a long derivation, right? So what we are going to say is, looks like nobody remembers. We did some derivation earlier in the first chapter. So if I had minus q here and plus q here, and this is my axial line, right? So you remember we did some derivation for this point electric field, this being L or A, something like this. So you must have arrived something like electric field at this point is equal to 1 by 4 pi epsilon naught 2p by r cube. Okay, so if you don't remember, you will have to go back and study this. Okay, so try to compare this and this. So what we are going to say is, that is electric field, this is magnetic field. So look at this one. So if I rewrite this, mu naught by 4 pi 2m by r cube or x cube. You know that this is nothing but constant, so the same thing here, right? In place of 2, you have 2. This is, what is P? Electric dipole moment. What is M? Magnetic dipole moment, right? So we say, and then R is this distance from the center. What is X? This distance from the center. So both we can see some similarities here. So what we are going to say is, this is nothing but, it's acting like a magnetic moment, magnetic dipole. This is a similarity here. we say it's very similar to the electric dipole on its axial line, E due to electric dipole on its axial line. However, we have a separate information. For bar magnet, you will be arriving at something like this. Okay, so even though it's not given here, so we simply say, since we got this value, right, it is similar to a bar magnet. Okay, because the bar magnet will have a equation like this. How can I explain it better? So suppose if I had a south here, if I had a north here, right? So this is electric dipole, this is magnetic dipole. So if I had a P here, what is the magnetic field at this point? So that is given by electric, this thing is given by this formula, magnetic is given by this formula. So this is derived separately, right, which is not given in your book. So we already know that B of this for a bar magnet is given by mu naught by 4 pi 2m by x cube, meaning this is my x distance. I don't following that. This is for electric dipole, this is for magnetic dipole. Now what we did was, we did some derivation, we started from here, we arrived at this one, which means this is same as this. What does that tell you? It tells me that this can act like a bar magnet. Okay, that's what it's telling me. So I can say this proves that current carrying loop is equivalent to a magnetic dipole. To make it easy for your understanding, write it down as bar magnet. Magnetic dipole is somewhat like a hi-fi word, so it's a simple word is bar magnet. Okay. Any issues so far? So this we are doing 21. And this is for axial line, right? So what do you mean by equatorial line? Same. This is axial line, where is the equatorial line? This way, right? That's what you must have done. So similarly, equatorial line for bar magnet will be somewhere here. So we are not doing a separate derivation, but we are going to say based on the similarity. Do you remember what we got for the equatorial line? Anybody remember? This 2 will not be there, right? For axial line it will be 2, but for equatorial line it will be plus. Axial line is more stronger, right? So this will be 2 times the equatorial line. So that means I can say based on the similarity. So based on the similarity, we can say on equatorial line, okay. So just rewrite the same thing, maybe I will write it here. So B is equal to mu naught by 4 pi m by x cube. Okay, you will get a lot of numericals based on all these concepts. Okay, only if you know the concepts, you will be able to attend the numericals. So the question said somehow show that it is equivalent to a magnetic dipole. So we started from this. We simplified it in such a way that it is coming to a bar magnet's magnetic field. So we are saying this is equal to this, which means it acts like a bar magnet. and this is for axial line, this is for equatorial line. So maybe here write it down for axial line. The other day we did a solenoid experiment, right? We flowed some current in the solenoid, right? Remember what happened? It was acting like one side it was north, the other side it was south, which means it's not only a loop, even a solenoid will also act like a north and south. What do you call a north and south? Magnetic dipole. So solenoid will also act like a magnetic dipole. Okay. So that's what is the next question. I think I forgot to give it the prove that a solenoid can act as a magnetic dipole. It's the same concept. Okay. So it involves a little bit of integration, okay, but it's not very hard. If you understood the previous one, this is also very easy. So I'm going to show a solenoid, something like this. So I'm going to take this as length L, this side is another length L, right? Put it in the center. So imagine I have some coils wound across this, right? So show it a little bit lightly. And the radius here is taken as A. This is the axial line. So I want a point P. So I want to find the magnetic field at this point P. So if I consider a small, so this distance is considered as R. I'm going to consider a small region which is dx, okay, which means it has got a lot of windings inside this small region dx. Of course, you have windings everywhere. For integration purpose, I'm going to consider small dx first. And this distance is taken as x first from the center. So you know that already we have found, suppose if there was only one turn here, right? And if this was the magnetic field I want at this point, right? So I can say B is equal to mu naught by 4 pi I 2 pi a square divided by a square plus x square. But in that case, remember, when you said x square, it was the distance from this point to the point P, right? It was from here to here. This is what we took it as x. Now, since the distance here is different, look at this. So this is my r, this is my x. I have taken this as r, this as x. So what will be the distance between here and here? It will be r minus x. So instead of this one can be replaced as mu naught by 4 pi I 2 pi a square divided by a square plus r minus x the whole square. Okay. So we are just, it's not equal to, I should say, this is replaced with this. But remember, I said it is only for one turn, right? If I had 100 turns in this small gap, what should I do? Multiply by 100. So that means I have to put a capital N here. Remember, N. I have to multiply by N number of turns. Whenever we put this capital N, remember we will bring in a small n, right? So small n is n by the small n is number of turns per unit distance. So in this case it is actually dx. So you generally put number of turns by length, that is your number of turns per unit length, right? So in this case, since I am considering only the small dx, right? So I can say n is equal to n by dx. Okay, so these things take it in the side. Okay, only then it will make sense because this is the main derivation. So I am going to say this capital N can be replaced as n into dx. So I am going to say I into n into dx gives me the total number of turns. So I into n 2 pi a squared divided by a squared plus r minus x the whole square. Right? Mu naught by 4 pi is a constant. But carefully listen, this is only due to the small distance dx. Okay, the small part of the solenoid which is called as dx. Because of this, it is giving some magnetic field B. So instead of calling it as B, can I call it as dB? Because this dx is providing this dB. Okay, so instead of calling it as B, I am going to call it as dB. So a proper explanation for this is small dB due to a small part of the solenoid which is dx. This would be the proper explanation. I am considering a small dx and I am considering what will be the small dB due to that, which means I have to take I 2 pi a squared plus r minus x squared. Only thing I have to multiply by number of turns. So number of turns is coming by small n into dx. Small n is number of turns per unit length. Okay, so if you have doubt. So anybody having any issues here, I think this is where many people might find it confusing. But I think we have done this. Anybody having any issues? If you have any doubts, I can explain it. If I say in 1 meter you have 5 turns, 5 per meter, right? 5 turns per meter. So if I say 2 meter, then how many turns will that be? 5 into 2. If I say half meter, it will be 5 into half. So that means if I say dx length, what should I do? N into dx, as simple as that. So simply you have to multiply by dx. So this is the number of turns per unit length. Okay. So maybe write it down somewhere here. I think this is a tricky part. If you understand this, after this it's very simple. Okay, the derivation is extremely simple. So let me write it on the E into n dx 2 pi a squared divided by a squared plus r minus x the whole square, right? Usual formula is a squared plus x squared. Here instead of x, we are considering only the distance from here to here, r minus x. Anybody having any issues with that? So basically, whenever you have dB, if I want the total magnetic field, what should I do? I should integrate, right? So that means I'm going to integrate this. So that means I will get d is equal to integral of this. So mu naught by 4 pi is a constant, current is a constant, number of turns n is a constant, 2 pi is a constant, a squared is a constant, radius, right? Only the dx is changing. Dx. Here r and x, I think we are going to consider x, L and A are very small. So just like the previous assumption, right? Assume A comma L is very small compared to R. So R is, let's say, it's like a faraway distance compared to this small radius and small length here. Okay. That means what can I do? Why would I do that? Because I want to ignore some of the terms, which means this can be ignored, this can be ignored. So I get only R squared. missing something here. So here also nobody told me I'm not supposed to have 3 by 2. That means everybody has started sleeping, it seems. And she didn't tell me. Right? You keep saying it to yourself, how can I? Shanai, Amrish, Jevin, what's the issue? So if this is very small, right, A and L, this is going to be gone away. This is gone, right? Sorry, R is, X is gone. So R square, square cancels, so I'll get R cube. So I'll get R cube here. So I can say A squared X ignore. Okay. If I integrate this small dx, right, from here to here, what will be the total length? 2L, right? Simple. So it's minus L to plus L. So you will get 2L. So if I integrate this, so I have to integrate from minus L to plus L, right? If you have a doubt in that, you can go by mathematics, or else you can go by this. So minus L plus L. So I substitute L minus L, which means you'll get 2L, right? Or you can simply physically see this. So if I integrate, if I add all the small length, I will get 2L. Or you can do it by mathematics, upper limit by lower limit. Okay, following that? So that means I'm going to say this entire term mu naught by 4 pi I n 2 pi a squared divided by r cube. So I think by the time you do all this mathematics, right, you will be forgetting where we started. What was our target? What did we want to prove? It acts like a magnetic dipole. That was our aim. Any idea how to prove that? You already have a clue from your previous. So carefully listen to this. So mu naught by 4 pi r cube is also there in the formula, right? In the previous formula. Somehow I have to make this into 2m. Any idea how to make this? What can you say about this one? This is a. 2a is there, right? So I into a. But what about this n into 2l? What is n into 2l? Number of turns, total number of turns. I told you, if it is only one turn, it is Nia. If it is number of turns, it is Nia. That means n into 2l will become Nia. So I can say I into a, and then there is a 2 there. So 2 can be written separately, and then n into 2l becomes total number of turns. So which is your n. That means this Nia becomes m. So mu naught by 4 pi 2m divided by r cube. In the previous case, I think I took it as x. Here I have taken it as r. Doesn't matter, as long as you get the same term. So have we proven what we wanted to prove? Because I already told you for bar magnet, this is a formula. Okay. So that means from this I can prove that solenoid acts as a magnetic dipole. So only thing is, since you have a lot of number of turns here, you are getting Nia instead of Nia. So the integration part may be slightly confusing. Okay, as I said, understanding it is easy, but how you are going to remember it, that's the tricky part. So you have to practice it many times. I have seen sometimes some students are very good at remembering things, so they will be able to reproduce it very well in the test. But some of you may find it very difficult to remember these things. So for your CBSE board exam, you will have to remember this. Only if you know the starting point, you will be able to arrive at the final answer. So all derivations, as I told you, you should know the diagram, you should know the starting point, you should know the ending point. So if you know this and this, you can always play around with this and arrive at the answer. So that brings us to the end of this block.